So hello, good morning everyone. So probably we are meeting, I'm meeting with you guys first time, and yeah. So since the quiz one is over, so can you guys comment how was the quiz one?
A lot difficult. Couldn't solve a lot of questions.
Okay. Yeah, it would be a bit lengthy, like what I observed in the discourse. So any other comments?
So I guess the result will be out on 6th of February, right, Jimmy?
Yeah, I'm not aware of that.
Okay, so yeah, on 6th of Feb, I guess, by the evening 6th of Feb. But the questions were pretty, like from the week first, I guess the questions were pretty simple. I don't know about the second, third, and fourth week.
No, all the questions were simple. Just it needed a more practice.
Okay, more practice you are. Okay. So
At
have you
least
went?
for me.
What?
That was the case, at least for me.
Okay. So have you went through the lecture week 6th and week 5th? Like everybody has went through the lectures of week 6th and 5th week.
Yes, sir, we have went through the lectures.
So okay.
Yeah, what is your feeling about the week 6th?
So week 6 is a bit easy.
Okay, week 6 is
The tutorials are nice in week 6, as like you have solved the questions, so we are able to do the things with examples. So that's why.
okay. At least a different view we got from like last batches. Last batches.
Yes,
No,
sir.
sir, I personally can't understand week 6. I can't understand anything professor is saying about PCA.
Yeah, it's okay. That is the regular comment which we got in the like last batch also. Like the week 6, what we got the feedback from previous batch was like week 6 is the most difficult week among all the weeks of MLF. Okay, so yeah.
Sir, I also found week 5 more difficult than week 6. Only thing is that week 6, once I find the eigenvectors and come ahead, and then I have difficulty finding the error J and the reconstruction error.
Yeah, that is what like sir has covered. Like sir has covered in the lectures derivations and all. So the most part of the lectures goes to these derivations only.
Yeah. So even in the problems of tutorials, they've not exactly told that how they have arrived at that solution of getting that error. So those steps, I would like you to actually explain how to do that.
Yeah. So we have also planned like to do, and we will cover like in conventional way this week 6. Okay. So
Thank
because
you,
yeah. So how earlier, what was the pattern of our live session was we won't do like that for week 6 particularly. So what we will do, like first we will start at from 11:05. Okay. So what we have planned is like we will divide we have 2 sessions, no? This one and the second session is on Saturday. So what we will do is like we will divide the whole week in 4 parts. Okay. In the first part, we will introduce the basic terms like what is PCA, how it works, something like that, geometrical interpretation. Then in the second part, we will see like we will know what is our first point and what is our last point. Okay. Then this we will connect the dots. These dots will be connected in the lectures, like what sir has done. Like we have all the middle steps in the search lecture. So we will cover that in the next session. Okay. Why we will do that? Like we will show you what is PCA, why it is necessary, and after that, like what PCA does, like what are the steps. These things we will cover today, and after that we will allow you, like whoever isn't as you said, like many of you didn't understand the like how it works. So then we will allow you to go through that lectures, and if you are comfortable, then it's okay. Otherwise, also like in the next lecture, we will cover, like we will do the derivation in some easy manner.
Sir, would we be covering some part of the week 5? Because I don't think the SVDs were covered last time.
Yeah,
Okay.
we had planned to cover week 5 also in this session, but unfortunately that instruction is not available with us today. So maybe some other day we will cover that.
So what happened? Yeah.
Yeah.
So Ram is not available today. So in the next session, or maybe we can arrange one extra session for that week 5, whatever is left. So maybe in the Saturday session, we'll first go through the week 5 content, whatever is left, and he'll
Yeah.
discuss the practice and whatever the topics is left, he will discuss the topics and then he'll go through the questions on the Saturday session. And the left time we'll discuss about the week 6 also. So today we are going through the basic part. Like many of you would be having difficulty in visualizing the PCA part. Okay, so we'll see the how generally we implement the implementation part we'll see today regarding the PCA, so that after this session, if you'll go through the lectures, you'll be able to understand why we are taking the eigenvalues, why we are taking the eigenvectors, those sort of things you'll be able to like sort out. Like many of you would not be able to sort out why this proof is going like in this way. Okay, so today we'll try to visualize the PCA problem, and then you'll go through the lectures. Then you can, I am probably like hoping that you'll get through, you'll be able to crack that why we are, how we are doing that proof and all. Okay, and after watching that video, again, we'll discuss like if you are having difficulty in that proof also, we'll go through that proof also on Saturday session if you are having difficulty. Otherwise, we'll go through the other parts, whatever you'll tell. Okay, so one guy is asking if you got the feedback about the video in the last term, why haven't we improved? Okay, so last term we were not having much student in MLF. Last time the number of candidates in the MLF was not that high. Okay, so that's why we have not implemented. But the thing is, okay, these parts like PC and all is bit difficult only. The maths parts of MLF is bit difficult only. Like everyone, whoever will teach, like I am a student of IIT Madras itself. I was a student. Okay, the same faculty I also went through and the same lectures and all. So there is no like bias thinking these videos are not that good. Like I have went through the same lectures. Here, at least we are here to like we are here and interacting with you. Okay, so when I was in the IIT Madras, nobody was there. Only the lectures was going through. If you, I can assure you, if you go through the offline lectures also, the same things will be teaching the same similar way. Okay, in the IIT Madras also, the same faculty I've read from the same faculty, IIT Madras, the ML course. Okay, so there is no biasness. Like we are not providing the best content. Like we are providing the like in this we are having the 3 faculty. So maybe the thing is that this parts is bit difficult itself, like the maths parts of everything is bit difficult. Okay, that's why you're facing the problem. You can like yeah.
I would show you one post, like a recent post I have read on LinkedIn. It was from IIT Delhi professor. So I would like to refer you that post. Okay, but before that, I will tell one thing. Yeah, as Vishal said, yeah, the main thing is like sir is assuming many things, yeah, which you would be already knowing. So that's why this kind of difficulty is coming. Okay, I'll just show that post. Like I intentionally want to show that. So whether my screen is visible? Hello.
Yes.
Yeah. So how a false love for AIML is destroying our engineering college. Okay. So yeah, Smriti Sarangi is a IT Delhi professor. So he was talking. I'll share that link because we won't discuss that much. So what I want to show you is like, yeah, so many people are doing ML, and what the mistake they are doing, like, yeah, most of they don't know what is going through beneath that algorithm. So what he is talking here is like, yeah, just what you will do, like there are many research papers publications going on. So what people do is like, yeah, just there is an algorithm, they just write just see it, just run the Python code, show some result, and voila, you are all done. So he's talking about many professors, like he has met with many professors in different college of IIT, IITs. So different, not IITs, like different, different university professors. So he's saying like, they don't have even a clue like what is Gaussian, what is Jacobian or singular value decomposition. So what most of the people, what people are doing like is just run the Python code, so some result, and voila, you are all done. Okay, so I'll share that this link. Okay, so what I'm saying is like, you guys are just learning the math behind those algorithms. So it's not obviously it's not an easy thing. Okay, so because many people don't even know what is going on. They just know that this is the algorithm. Just 2-line codes are there in the Python. Okay, you use the library, you just get the result. That's it. Many people are doing like that only. So that's why like he has written like how for MI AI and ML is destroying our engineering college. Okay, so I'll save that link. Okay, you can go through this post. So let's start with this. So as we told, like we will discuss the first this like for initial point of PCA, initial point of ML, and final point of where we want to reach, like what is our PCA algorithm and how it works, and we maybe later in the next session, or if time permits, like we can take that also, we can cover that also in this session only. So we will but it's okay, you can go through after this session, you just go through that lecture. If you are able to understand that, then well and good, and otherwise also we will cover that in the next session. Okay, so so
If
these are
somebody has not seen the week 6 also, he'll understand everything, because we are just discussing the basic part of PCA and visualization thing, so that it will help you to understand the lectures. Okay, so whoever has not seen, so somebody is messaging me if he has not seen the lectures, so you must like attend this session. It will help you in understanding the lectures. Jimmy, go ahead.
So don't worry, I will assure you that you will learn each and every bit of this this week. Okay, and you will be ready if you are going through these 2 lectures, like this session and second live session, you will be ready with for PC part completely. Okay, so first I am assuming is like okay, so these are the things. My screen is visible, no? That content was.
So we can see the LinkedIn post.
Okay. Yeah. I had opened. So is my screen visible now?
Jimmy.
Yes, sir.
So these are the topics which sir has covered in this week. Okay, positive definite function, positive definite matrix, PCA, and how we derive that part by using maximizing variance. Okay, so obviously many of you are at different steps of this ML skill. So I'm assuming all of you are at first step only, like you all are novice. Okay, so like that only we will start. Like what happens in machine learning, we will just start we will talk about the each and every term. Okay, so you got a data set, what is just say you have to predict a price of house. Okay, so what we call each and every term, I will just the ML jargons, I will just go through that, then we will go to the main point. Okay, so you got some data set which is like something like you will get some this kind of table only. So suppose you have to predict the price of a house. Okay, so you have to make a system or model which will predict the price of house. So you have got data like you know the house area, you know the location, you know how many bedrooms are there in that house, what is the distance from hospital, distance from airport, or and some other features. Okay, so based on that you will predict the price. Okay, so what we call this, the whole thing calls we call it as a data set. These things like these are called as features, and this is your target variable. Okay, and like your 1 2, these are samples. Okay, samples, we call it like that only, or you can call it also, we also call it the first instance. Okay, so I think now you are aware of the basic terms. Okay, so okay, we will cover that. Okay, and then we do 2 type of prediction. Okay, First is the regression and second is the classification. So in that question only, like if I ask you to predict the price of house, that will be called as regression. Okay. And if you call it like the predict the house is costly or not, like in class 1 or class 0 type, let's say we assume that more than 5 crore is class 1, yes, or more than less than 2 crore is, or take it like less than 5 crore is no. Okay, so something like that, yes or no type, or but means you have to divide the all the in few segments, that is classification. Okay, so now the term comes ML jargon, dimensionality. Okay, in ML it simply refers to the number of features. Okay, so this is the dimensionality. Like if I'm just talking about the up to distance from airport only, like then 1 2 3 4 5, we have 5 them, like 5, it is placed in the 5D. Okay, dimensionality is 5, something like that. Number of features, that is called as dimensionality. Okay, in variance it is measure of how spread out the data is. Okay, that we will also see later. Okay, so this much is okay. Okay, now we will come to the basic definition of PCA. What PCA does, it is just a dimensional reduction method often used to reduce the dimensionality of large data sets. So from this example only we will discuss. Okay, so these are the data you have got. So what I will do, why I will say is like how regression works is like it makes what regression do is like it makes the equation like price equals to something into house area plus something into location plus something into number of bedrooms, something like that. It makes a large equation. Okay, since we have many features, so this equation will be large. So what I'm saying is just you select a few most important parameters, most important features from this. What would be your answer? Hello.
Maybe the house area and location, number of bedroom.
Price.
Price. We have to predict the price. So you just I would ask
House area, location is the most important.
Okay. So
Number of bedrooms.
Just I will see all of these are important, but so few are like more important, few are less important. Okay, so something like that. Whatever you said, that's correct. So I am saying that you can select only 2 features from here. Okay, and based on that you have to predict
number of bedrooms.
Which one?
Location and number of bedrooms. That means split area will come. Location means little posh area will have more costly.
So like that you selected these 2, no? Okay.
And I think that number of bedrooms would be kind of correlated with the house area.
That is also correct. So these 2 points only I wanted to cover. Whatever you told, I would that would,
same house area we can have double bedroom, triple bedroom also with the different costs.
That would that was my next question, but it's okay. That is the as you said, this is what PCA does. Okay, PCA selects those kind of axes or features which has the most impact on our target variable. Okay, so as you guys said, as he said also, like house area is proportional to number of bedrooms. Like these are correlated. Obviously, more will be the number of bedrooms. Indirectly, it's not like the high correlation coefficient will be 1, but we can assume like it would be more than 0.8 at least. Okay, so we are assuming just for simplicity or anything, whatever you said, we are taking just two variables. Okay, location and number of bedrooms. Okay, or location and house area. Okay, any two, that will work. Okay, so what PCA will do is just like you, as you said, like these 2 are important factors. Okay, based on that we can predict the price more or less. But more close to the accuracy. Okay, it will be more close to the accuracy. So that is what PCA will do. Okay, it will just select some features, and the main thing is like it doesn't select from your features. Okay, so here you are able to see that these 2 things. Okay, like that we will do, but the PCA does like he draw his own axis, like he create his own features. Okay, and based on that he tries to predict with minimum number of features. He tries to predict them he tries to give the maximum accuracy. Okay, so like that only. What the second sentence is, by transforming a large set of variables into a smaller one that still contains the most of the information in the large set. So I think you are clear with this point also. Are you clear?
Yes.
So now I think all of you are able to understand like what PCA does, what is his job, So that is, and now the question is why we want to reduce the dimension. So just don't read all this stuff. Just read the first sentence. Like large dimensions are difficult to train on and need more computational power and time. Okay, that is what I was saying. See, here if the equation for price becomes like just take it as a x1, x2. Just take it as x1, x2, x3, x4, x5. Okay. So it is just take this one assume it y equals to 5x1 plus 3x2 plus 2x3, something like that will be the equation. So just think like how large that equation will be. Like here we have 5 features, and so then the equation will like y equal to 5 something x1 plus something x2 plus something x4, something like that. Means it will be large. And after PCA you got these two only, like these two features only. So now our equation will be y equal to 5x1 plus 3x2. That is very simple equation, no? So like that only, that is the main job of PCA, and that is the main need of PCA. Like that, large dimensions are difficult to train on and need more computational power and time. In this one, here we are at least we have here we are putting just 5 dimensions. Okay, just 5 features. Just assume like when we have 700, 800 features. So at that time, how difficult it would be to train the model. Okay, in that case, PCA works. PCA works very well. So that was the job of PCA. So how now the second question comes, like PCA will do and how it will do, something like that. So in this one, just assume this as just a matrix. Okay, just forget the above term, just forget this one. It's just like this blank. This is just like a matrix, no? Hello.
Yes, sir. Yeah.
It's just like a matrix. So what it will do, like just here take it as a like a 7 cross 5 matrix. Okay, 3, 4, 5, 6. Okay, 7 cross 6 matrix. Okay, so what PCA will do it like it will, if we ask PCA to make it in 2 dimensions. Okay, just take 2 features. So what PCA will do is like it will return the 7 cross 2 matrix. We will give input as 7 cross 5 and it will give result as 7 cross 2. If we'll ask PCA to give just one just plot all those things in 1 dimension, okay, then it will give the matrix as just 7 cross 1, something like that, 7 cross 2, 7 cross 3, or whatever we will ask PCA to do, we will do that. Okay, so now the question is like input feature matrix, we gave that as an input, it transform it and it gave you the output matrix. Okay, sometimes you just ask them to just transform the matrix like a 7 cross 5 you give and it will give you the output. If you will ask for 5 number of columns, then also it can do that also, like it will give you the 7 cross 5 matrix. Okay, so then the question is like why we need PCA, and sorry, that we covered. How it will do that and why that method works. So these 2 questions we have. Okay, so these 2 questions which is covered in our lectures, sir's lectures. Okay, and so here we will cover that geometrical interpretation part of these 2 things. Okay, so okay, let me see. This one. Okay, so what we did is like just for this case we assumed like we have just 2 dimensions. Okay, like we have 2 features only. Here we have already assumed that we give input as just a number of a house area and location. These 2, just take it as like x-axis is plotting house area, y-axis is plotting location. Okay, and we got we plotted all the points, like all the matrix values. So we got something like this kind of scatter plot we get. Okay, so now our PCA is asking, 1 second. Okay, so now our PCA is saying that we asked our PCA to do just give me all these features, all these values on 1 axis. Okay, so it will try to plot here in this question we have asked it to transform it on the 2 by 2 only, like input was also like a suppose n cross 2 and output is also n cross 2 only. Okay, so what PCA did is like it tried to plot the axis in such a manner that it covers the maximum point, okay, and with the least distance, something like that. Just see it like PCA is allowed to create a road, so that and just take these points just like your friend's house, okay. So and you told PCA to build a road from which like all my friends' house is closer, okay. So to do that, what PC will do, like it will create a road which in such a manner that all the houses are very close to that road, okay. And we asked it to just plot a one road, so it did like that, okay, in this axis, okay. If you ask that PCA to build two roads, so in that case it will make this type of road, okay. So that is what PCA did. Like
Sir, is it like a best fit line for single line, single
yeah,
road?
something like that only, like as you said, no, something like that only, like it is not fitting the line actually, okay. It's just we are talking it.
Hello, sir.
Yeah, hello.
Hello. Yeah. So the PCA is doing like it is taking a matrix and it is giving the output as like basis. So which basis is best fit? Is it?
Yes, like that only, like best fit. How we calculate that best fit, that for that only the other terms, but don't use that ML jargon for now.
No,
That is
sir. I'm asking that it is giving a line or basis. So what is the actual output?
basis. Okay,
Okay.
and yeah,
Okay. Thank
I'll
you. Yes,
cover,
sir. Thank you.
yeah, I'll cover that. Okay, so like that only, like you just plotted a road, okay. So you plotted a road and you took all the data points according to that road only. So this is the, if you will ask to plot just one axis, no, it will plot this axis, and in PCA we caught it as the first component, okay, and this will be the second component. So you can assume like if you will go through this road, the error term we will cover in the further slides, okay. So this was the, so that's how it transformed. So here the our yeah
Continue.
here our data are plotted on, yeah, as I told you, the two features are there, like x1 just assume that house area, and x2 is just assume your locality, okay. So the all the data points are plotted here. So the PC what did is, okay.
Sir, at a time it can plot only two types of data. It's not three feature.
No, nothing like that. So we will cover that. Don't jump. Okay, I'm just trying to just
Okay, sir.
Okay. Yeah, with each and every step. Okay, so when I was trying to rotate them. So yeah. So just think like that. Yeah, all the data are plotted on, yeah, here just two dimensions only. Like the, as I told you, the area, and second is your location. Okay, so the data points are plotted. So what PCA did, like it just rotated this and it plotted its own axis, okay. This is as we see here, no, like that, like the PC1 principal component 1 and principal component 2. If you'll ask that to just see, we will ask that to just to plot it on just one axis, so it will take the red one only, because that is the first first principal component, because it contains the maximum information, okay. And if we ask it to plot it on the two dimension, then it will use that second year PC2, okay.
Sir,
Principal component. Yeah.
So can you explain this part again? Like, why is it rotating the data?
Okay. Wait, Jimmy, I'll take this. I'll try to explain this once again.
Yeah.
Okay, so I'll share my screen for once. Can you stop that, Jimmy?
Yeah.
And so is it like there are two best fit lines here?
Yeah, I'll just in the further slides, just hold your, what I'm saying, like just hold your curiosity. We'll cover everything, okay, like that. Whatever you are saying, just we will cover in the next few slides only. Like why do we are doing that, and what is, we are just creating that intuition, like.
Okay, so what you were asking, see, PCA generally what, if we are having two features, for example, I'm having two features now, just two features I'm having now. And if I have to convert that, like the data set you are having, see, for example, I'm telling the one feature is, what was the first? Okay, I'll take some other features, like I'm having one height as one features. I'm just summarizing whatever Jimmy has told. I'm taking one as height features and one is the blackness of the hair. So what will happen? The blackness of, and we are having a data set of the like Indian peoples. So mostly the blackness of the hair will be almost same for the Indian peoples. Like mostly it will vary from gray to black, right? So there won't be that much of variance in the this features. Like if this is a feature 1 and this is a feature 2. Okay, so the blackness of the hair will be almost similar. Like in the way the Jimmy was telling you, if we are having some two features, one feature is not that the spread of one feature is not much. Like I'm for example, I'm taking some like some data points. These are the data points we are having. Okay, so now you can see what is the variance, like what is the spread of the features 1. The spread of features 1 is this one, right? This much only. And the spread of features 2, that is the height of the person, like whatever the data set we were having, like x1 to xn. And this is the features 1 and this is the feature 2. This feature 1 is the blackness of hair and this is the height. So what happened here? So see, you can see the spread of this feature, the features 2 is this much, right? So the spread of one feature is very high and the spread of the second feature, the blackness of hair is very low. Okay, so if I have to convert that, like for example, if I have to convert this into one dimension, which one I can remove? If I have to remove one features out of this, like F1 and F2, I can remove the features which are having a list spread, right?
Sir,
Yes,
but
sir.
it depends on what you're trying to predict, right?
Hair color you can remove. You can remove.
Like yeah. So I'm trying to predict anything you can say, like it's a classification problem or regression, anything I'm trying to predict out of F2 and F1. Like if features 2 is height of a person and 1 is the blackness of the person. Okay, I want to predict anything. Like for example, I want to predict the weight of the person. Okay, anything like that. So the features first, what is that was the blackness of the hair, that the spread was very less, right?
Sir, but how does the variance relate to how much information that feature has?
See, if I'm like, for example, that example we were taking, like the price, we have to predict the price of the house, right? So
Yeah.
if I have the features like the area is here, and this is the number of bed.
Yes, spread of number of beds will be less.
Right? The number of bed would be lesser, right? So we can remove these features if I have to convert this two features into one dimension. Like for example, I'm taking only two features here. If I am having thousands of features, so how can you visualize that? You can't visualize, right? 1,000 features in a figure in the 2-dimensional, but you have to visualize a 1,000 features in 2-dimensional. So what we can do, we can take out the two most important features out of that, like not two most important. We will just try to convert that 1,000 into 2-dimensional, like in two directions, such that in this 2 direction, the variance would be like the spread of the data, would be most, right? The spread, or you can say the variance is most in the 2-dimensional. So two vector will be tracking, and in that 2 vector, we will take out the two F1 and F2 and we'll try to visualize that so that the information will not get lost. Mostly we'll try to grasp the information and we'll try to reduce the features out of 1,000, right?
So just sir, one second, sir.
Yeah.
Just can you correlate? Can you analogy taken like in vectors? Suppose there are 3, 4, 5 vectors. We can take the components along x-axis and y-axis, and you can find the resultant. Is it correct or not?
Yeah. See, if I'm having features like this, see, for example, if this is feature 1 and this feature 2, and the data set are like this, like the Jimmy was telling you, if I'm having the data set like this, right? So what we can do, we will try to find one vector in this direction. We'll not, okay, in this direction only, like for example, this is U1, right? And this is the second direction, U2, right? both are orthogonal to each other. So in this direction, you can see the variance is most, the spread of the data is most, right? And in this direction, the spread is very less. So if we'll try to make this as a one, like you can say one base, and this is as a one, you can say a base, or what you can say, we'll try to rotate this in this direction. So we'll make this as a U1 and one as U2. So in U1, the spread is very high, and U2, the spread is very low. So if I have to convert that in one dimensional, then we can remove that U2, and U1 will be the most like impactful, you can say the vector, right?
But sir, what about other data, like above second line? So some data is on the line of U1. What about the data above?
So we are not, see what we are doing in PCA, we'll like cover it in the later part. What we are doing, we'll just take the projection of all this data and we'll try to make other data out of that data. Okay, if I am having this data, so we'll try to project this all data on this U1 and U2. Okay, if I have to convert that in one dimensional, what we'll do, we'll try to take the projection of this data on this, like whatever the vector we are taking. Okay, this in the later phase we will come to know this is the eigenvector out of, like if I have to convert that in 2 dimensional, we'll take the most like the value of the eigen vector which are having the most like value, like if lambda 1 and lambda 2 is the two eigen value. So this eigen vector will be consisting of the most information, and this will consist of lesser information out of the two. Okay, so this will give us one vector v1, and this will give us one vector v2. So this is v1, you can say that this is u1 or v1, this vector is in the direction of u1, and this is a v2. If I have to convert this into one dimensional, we can directly take this v1, this vector v1, and we'll try to do everything on this v1 one day. Okay, so are you getting the point now? Till now?
No, sir, not really. Like, why are you rotating that plane? I don't get, like, why are you rotating U1 with the data
I'll just
points?
try to visualize that. Okay. So yeah.
The visualization is clear, but what is the purpose of that?
Okay.
If you do not rotate, still it's the same. Like the data does not depend on the axis the rotation of the coordinate system.
Yeah,
like
but
coordinate system can be anything, right? We are rotating because to understand, like it is easy if we visualize that the axis is rotated. Otherwise, it's the same.
That's easy for
We are
us,
just
but for computation.
shifting our axis.
Yeah. Okay. Why we are doing that? Just as I told you, no. Just stop that. Okay. Or if you want, yeah, later you can share that.
Yeah, you want to share something? Okay, I'll stop this. Yeah, I'll stop.
Okay. So again, we went to the same point only, like why we are rotating it, just to minimize the construction error and just to increase the variance. That was the point only. How we did that? Because just see, just think like only like, yeah, these all are your friend's house. Okay, you are standing at this point. Okay, so every time to go to this friend's house, you have to go from here to here. Okay, so that is your construction area, or you can say, yeah, this is your cost. Okay. Okay, so every time you go from here to here, okay, like that only. So what we are doing here is like we are just creating a road, and so we are making a road, okay, like that. And from here, like it is very closer, no, all the points, and we are able to reach. Just think like, yeah, your money cost of traveling is your construction error, something like that. Okay. And in the next slides, you will be. That is what our means of PCA was. Like it is just reducing the dimension. In that case, we are just transforming it. Why we are rotating it? Because we are transforming it so that it is all the points are more closer to our axis. Okay.
Sir, but okay, let's say you have the picture in the left and the picture in the right. The picture in the left would have the same variance as the picture in the right, right? Because you're just rotating the. So
see, the axis is also changing here. No, the axis is like what is the variance? Variance is the spread from the mean, something like that. No, yeah. So here you are seeing that it is varying from here, this point to this point. Okay, something like that. But here all the points are very close to the axis. No. So here you will get the lesser. You are able to cover the maximum points. Just see if you further more slides. Okay, we'll to show that. by visualizing that also. Okay. So the main point is the main issue comes here, no? Like you have here just 2 dimensions, so, and here we are converting it to the 1 dimension. Just take it like you just take it something like that. You have to create just 1 axis. So I'll ask you, this is all the points are plotted on 2 axis. So in which direction you will create a road, so that you will be just you have to create just 1 road, okay? And what will be the direction of that road, so that you will be more closer to all the points, like most close to all the points.
Okay, yeah, sir, I got it. But
Yeah.
it won't always rotate in that this direction, right?
No, nothing
Horizontally.
like that.
That might change.
Yeah, that might change. Yeah, suppose the points are like here are few points, here are few points, and but if these points are more denser, no, like here
Yeah.
just see, yeah, and here the more denser points are, then our direction will like that. Okay.
It will change.
Yeah, or something like that. Wherever, like it tries to what the main of this this road is, to reach at each and every friend's house with minimum distance, like something like that. Okay.
Yeah.
Yeah.
Thanks.
Yeah.
Sir, one question is there.
Yeah.
So variance is direct related to weightage. Means if some feature has more variance, then it will depend on more for prediction.
Yeah. For that reason, yeah.
Because we are reducing one feature,
Yes,
no, sir, which has less.
Yeah, that's true. That's true. Okay.
Okay, and that eigenvalue will be also more.
Yeah, that's
side.
all. Yeah, that's how it works.
Okay. Okay.
I'll just share one other screen. So is it visible?
Yes, sir.
Yeah. So okay. So here just see that all these are our original data set. Okay, like that we just plotted here, like 5 data points are there. Okay, and it is like that. Okay, so what here we are just reducing the dimension, like it's in 2D, like we have to make it in the 1D. Okay, so this is like here it is like as we said, like this is a house area, this is location. Okay, but it doesn't have any physical meaning, PC1, PC2. Okay, we are just plotting it on the 1 axis. Okay, so in that case, what will be your axis, like in which direction? Just forget this figure. Okay, just see here, these are the 5 points. So you have to build a road in such a manner that you are able to cover all the points with the minimum distance, like from that road. So what will be the direction of the road?
In the red line.
Yes. That is what our PC did. Like if we have to just make a 1 road, then that will be this one. Red one, that will be, which we called here as a PC1. And if we have to make 2 roads, then it will be just obviously it will be perpendicular to that one.
But sir, we could rotate on in the y-axis also, no? So red line will come vertical and green line will left.
Yeah, anything, whatever you do, just it is just a visualization. Just you have to assume that you have to build a road in this red direction. Okay, like that.
It is not necessary that we have to rotate only right.
Yeah, no. That here he has plotted PC1 in the horizontal basis, so that's why he has written that.
Yeah, means we could draw in PC2 also, no?
Yeah.
Okay,
no. That is the PC1. We will call that PC which has the highest, which is the most important. Like which has the PC1 we called the.
Then the name will.
Yeah.
Okay.
Yeah, that's it. Okay. So in 2D, you are able to visualize, like 2D. We converted 2D.
Hello, sir.
Yeah, hello.
Sir, a small question that we are in very fundamental level, so we are using like a linear axis. So in the practical scenario, is there anything like if the features projects and circular or something else pattern, then we have to take curvilinear coordinates or something like that in the practical scenario?
Yeah, in the practical scenario, like that's when we have the large number of dimensions, then only this covariance matrix comes to help us. Okay, so we are just building that step. Okay, in the 2D you are able to visualize, you are able to convert that in 1D. Okay, so let's go to the 3D part only. Okay.
See, and sir, I'm asking that is it possible to non-linear thing? Like, is it comes in practical scenario, the non-linear thing, or always?
This is axis actually. Actually, just see, these lines are just axis only. Okay, these lines are axis. So axis will be like that only, no? Like in the 1D, 2D, 3D, something like that. And more than 3D, even I am not able to visualize that. Okay, in that case only like we use the covariance matrix. Okay, so here just see that these are the points like in the 3D. Okay, so what PCA will do here, like you have this axis like X, Y, Z, this black one. Okay, just don't see this red one. Okay, the red, blue, and green, red, blue, and green one. Okay, just we have this axis like all the points. These are the data points. This purple one. Okay, and we have axis like X, Y, Z axis. Okay, so all the points are here. Okay, so what we have to do is like we asked you the questions like you have to plot this in, or we told the PCA algorithm to just plot it in one axis. Okay, then what will be the axis? Okay, just tell
The 45-degree line.
Yeah. Okay, so whatever, or just think it like the lines which covers the maximum data point with the closest. Yeah, as you said, like the best fit line, something like that. Okay, actually that
Sir,
is not. Yeah.
Sir, if we drew like a 45-degree, two vectors in 45-degree, won't they cover the maximum distance too?
Sorry.
If we in the 2D thing, if we drew two vectors in 45-degree direction in the same image, like below.
This one.
The 3D part.
Yeah, 3D part. What?
So in the second image, on the right, if you from the origin, if you drew a vector at 45-degree, like y is equals to x line.
Yeah, y equals
won't
to
it
x line.
kind of cover the
So,
maximum distance?
No, just see. The thing is like it has calculated the construction error, and based on that, it has calculated the system. Like I haven't this side is showing this visualization, so they have plotted this like how these are on x-axis, like how it is varied along this axis, how it is varied along y-axis, and how it is varied along z-axis. Then it has changed it on PC1, PC2, PC3. Okay, just think like it has calculated its construction error, and based on that only it has plotted here. Okay, so what it did is like it has done his calculation based on that only, like he has plotted. So he is according to him, like this red one is according to if you have to plot one road, then that road will be this along this red line. Okay, so maybe the points like we are seeing like 1-2 points, but that is the points will be more dense towards this red line. Okay, so here it is converting just simply just 3D to 2D. Okay, so
one question.
Yeah.
Why is it taking written? Why not it's taking a 45-degree line, the best fit line, and converting that to horizontal line here?
So that is what I said, like I should not use that best fit line actually. Okay, this is the axis, just as someone mentioned in the comment, no, like we are trying to find some axis like on which the error is minimum, like for which the error is minimum. Okay, initially our axis was here. Okay, from here if we will calculate the distance, no, that was like higher as compared to this one. Okay, this one axis. So that is what we try to find. But here let's just to assume that like okay, we are doing that. We will just cover how this point comes in the next slide, in the upcoming slides. Okay, so like just think it like, yeah, these are the points, and you have made the axis like PC1, PC2, something like that, so that all the points are closer to this axis. And obviously it is just remember that PC1 will be always perpendicular to PC2, and PC3 will be perpendicular to this PC1 and PC2, because these are axes actually. So as someone mentioned at the initial step only, like
Sir,
yeah.
So I think you have to click on show PCA, then it will show. It changes.
Yeah, you are right. Now as we are able to see this one. Okay.
Sir, but in practice, these bases won't be this perfect, right? Like these are like at a 90-degree.
Yeah, exactly. That's the main issue. No, here up to 3 dimension we are able to see, because we don't know like how things looks in the 4D, 5D, 6D. In that case only, like how the variance term, covariance matrix comes to.
Can you show below 17D example?
Okay, just yeah.
They didn't draw any graphs, sir.
It might be 17D to 3D projection.
Yeah, sorry.
it might be 17D to 3D projection.
Yeah, correct.
Maybe. Yeah. But just think like, yeah, up to 2D, 3D, you are able to see. But if it will go beyond 3D, you won't be able to visualize that. That's so yeah, our visualization part will be up to here only. So in that case only our covariance matrix comes. Okay. So I think yeah, these things are just but we have covered already through the codes. Like we just plotted 2D graph points on the 2D space and 3D space. So yeah, that's not an issue. Like again here, we just try to just do that to get that accessible. So yeah, as I told you that the first paper cover, it is line in the diagram with the biggest variance. Okay, in this it was not clear in this picture, but yeah, as you saw, like your first principal component is the line in the diagram with the biggest variance. The longer line, obviously the first principal and component will be the longer line. Okay, the second principal will be the which has the second highest variance. Okay, so like that. So as I said, like why bother with calculating covariance when we could just plot the two values to see their relationship? So why will calculate this covariance? That's actually you are able to see the answer. So I think yeah. So why it is necessary is because the calculations are used to find relationship between dimensions in a high dimension data set. Okay, so usually greater when it is more than 3, then it helps us. Like it is where the visualization is difficult. In that case, we do this. Okay. So how we do this is like yeah, by finding the eigenvalues of the and eigenvectors of the covariance matrix, you find the eigenvectors with the largest eigenvalues corresponding to the dimension. That okay, just stop here also. Like we should not go to this word right now. Okay, also this again. Just let's go back to this our slides.
Sir, can you please share that column? This one, that Python sheet, collab sheet.
Okay. I'll share that also. Don't worry. Yeah, this is the same thing. So now our question comes like how we'll do that. Okay, we know like we have to plot some axis, and that is the job of PC, and how it will do that. Okay, so to do that we have to project our data on lower dimensions. So that is why we told me like here we are plotting the 2D to 2D only, like but just assume that we are not plotting this second dimension. Like okay, we are projecting all the data on the first component only, like on this first line only. Okay, we will try to do that. Okay, so in such a manner that construction error is minimized. Okay, now from here onwards we will think like we have the input as 2 dimension and we have to give output as a 1 dimension for our visualization purpose. Okay. Okay, I think yeah, the section we have just shown. Okay. So how it works? Yeah, this is the practical method. Like how we do that. I should cover that here only. Yeah. To do that, what we do here?
Okay,
yeah. Just wait. I think I should use that page only. Okay. So this is.
Is there any difference between the PCA and the least square method?
Yeah, there is difference, and the thing is, here there you were able to find that that least square error is just like a reconstruction error. Okay, so now we'll just whatever I told you, just keep it, and this screen is visual, no? This whiteboard.
Yeah.
Yes.
Yes, sir.
Okay. Let's take this one. Okay, so suppose we have this point, this, this. Okay, so now what we have to do is we have to take one axis, like just it's all the points are on 2D. Okay, we have to plot it on 1D, we have to project it on the lower dimension space, as the Tamka said. No, so we have to project it on the lower dimension space. So what we do is like we have to take a line or axis such that it that our construction area is minimum. Okay, so for that, just take it like we took this point, okay, to this line, okay, this as the axis, like our PC1. Okay, so it was the original data point, and we are just projecting it to the lower dimensional space. Means our PC, we are projecting it on the PC1 axis. Okay, so this will be, and according to the term, this was your x1. No, so this will be your x1 tilde. Okay, in this axis, okay, yeah, this on this axis the point was called as x1. Okay, but on this axis, just we are making it 2D. Just assume, just forget this, just assume that we have just one axis only. Okay, for this axis, this point is will be x1 tilde. Okay, like that only we will project all the points on this new dimension. Okay, so if it is x2, then this will be x2 tilde, and your construction area is this length. Okay, so our job is to just make this PC1 line in such a manner, draw PC1 line in such a manner that this distance is minimum, which means that the reconstruction error is minimum. Why it is called a reconstruction error? Because we are projecting the original data point to this dimension. Okay, that is what was covered in this picture. Okay,
But so this is same as a least square method, no?
yeah, this line, yeah, this is just same as your least square error only. Like as you told me, the least square, like the line which gives the, but in that case that was just a line. Here in this case it is a axis actually, or basis.
So here we have to find this direction. Okay.
Yeah.
But in that list square, you have to just find the line that will best suit the data set. Okay. Here you have to find the direction, or you can say the vector in this direction, so that the reconstruction error would be minimum. Okay. Or you can say you can do the similar thing with the variance, maximizing the variance also. So here there will be an optimization problem. Okay. The optimization problem is the reconstruction error, and the constant is that the vector is the like orthonormal. Okay. So with the help of that constant, we will solve the optimization problem using some gradient descent, so that we can find the direction of this line, the direction of this vector. Like you can say the vector we will find. Okay, this would be our optimization error. Reconstruction error, or you can say the constant optimization problem. And from here we have to find this vector. Okay, with the help of some constraint. That constant would be u. Like if I'm this direction is u1 vector, so u1 transpose of u is equal to 1. That will be our constant, and that we have to solve. In that solving that problem, that is been discussed in the lecture, how we generally solve the problem and how we'll come to a conclusion that u1 vector, that u1 whatever we are like taking, this u1 is the eigenvector corresponding to the maximum eigenvalue. Okay, if I'm taking only one out of these two features, I'm taking, if I'm have to reduce into only one features, then this vector will correspond to the eigenvector that is having the maximum eigenvalue. Okay, have you got the point?
Yes, got. Sir, can you repeat the eigenvector part only?
See, so we have to get this direction, okay, where the reconstruction error would be minimum. Okay, this is the optimization problem that we have to solve, right? X1 minus x tilde plus x2 minus x2 tilde, right? With the constant that this direction is orthonormal, like the direction, if there is a one more eigenvector that is perpendicular to this, so we are having u1 transpose, like if this is a u1 vector, you can say u1 vector, so u1 transpose
to find the perpendicular axis.
Yeah,
right?
we have to find this vector u1 vector, we have to find where the reconstruction error is minimum, right?
Yes, and it's orthogonal.
Yeah, it's orthogonal, almost. Yeah, it's orthonormal. So big orthonormal means if it is getting multiplied with itself, it's 1, the length is 1, and if that is multiplied with some other vector, then this product will be 0. Okay.
Yes, sir, got it.
Yeah. So this is the one method. The other method is the variance part. So should I explain that part? Jimmy?
Yeah, just let me go through that and later you
Okay.
can start.
Yeah.
Okay. So as
So one more question. So in this PCA, we'll first take all the features and then we'll find whichever has the maximum eigenvalue. Then we'll consider that only that one to reduce it. Is it like that?
yeah, like that. Just we'll cover that also in the next step.
Yeah.
Actually, you guys are just going just bit fast. Okay. So yeah, that is the main, like that's how PCA works. So I'm just trying to build the intuition. Okay, so our job is to just get aligned that PC1 principal component one line such that this it is just like a sum of x1 minus x1 tilde, x2 minus x2 tilde, x3 minus x2 tilde, and yeah, this actually the distance, it is you can take it as just the distance. It's not a correct one, but yeah, something like that. Yeah, this distance is minimum. Okay, the sum of all these distance are minimum. Okay, you have to take the PCA1 in such a way. Okay. So yeah, that is what we call like the minimize the reconstruction error. So what we are reconstructing it, we are transforming this x1 point into x1 tilde. So what is the reconstruction error? This line, and we are trying to minimize that. Okay. So I think yeah, up to this one. Yeah. Now the slides are visible or not? Hello.
No,
Still the whiteboard.
Okay. Let me check. So yeah.
Yeah, now it's
Yeah. So that's how that is what we will do. We have to just get this point. We have to just draw this axis in such a way that this reconstruction error are minimum, and just see it, just to see it in another ways, like variance of projected data is maximized. We shall cover that. Okay. So how we'll do that? The next question comes is like how we'll do that. For that only, like we have these steps. Okay, we first construct a real symmetric matrix using those data. Then we pick the top m eigenvalues with the corresponding eigenvectors. We use that to do projection, and in the end we maximize the variance, or alternately we can think at like it will minimize the reconstruction error. Okay, this in this slides we have mentioned it like just how we'll do that. Okay, in the more detailed manner, like we took that data set, we compute the mean of every dimension of the whole data set. You think what do you think, like what is the most important part in this one? Yeah, here. So for this column, okay, this column, all the columns are like feature vector, what we are saying, what we are saying there. So yeah, in this one, what is the most important part? Okay, so in this whole column we have the two important part, like based on that we can talk about this house area. Like first is the mean of all the house areas, and what is the variance of that house area. Okay, so what we do here is in the PCA, in the first step, in the first step only, like we just calculate the mean of each and every dimension of the data set. Dimension is nothing, just replace, you can replace it with the features. Like we compute the mean of every feature of the whole data set. Okay, then we calculate this covariance matrix. Then based on that covariance matrix, we calculate the eigenvector and corresponding eigenvalues to the covariance matrix A. Okay, and then we sort the eigenvectors by decreasing eigenvalue and choose k eigenvectors. This k will decide like how many dimensions we want to give to our output one. Okay, if we are selecting just one eigenvector, then it will be just like PC1. If we are selecting two eigenvectors, then it will be plotted on PC1 and PC2. Like that it works. Okay, so in that case you can say like what eigenvector does there. Eigenvectors are like just unit vector representing direction of largest variance of data. Okay, something like that. So yeah, Vishal, now you can continue. And as I told you, the distance between the original data point and its projection onto a lower dimensional subset. This is what we call as estimate. So this is your original data set. We projected it on the lower dimensional data space. Yeah, the distance between these 2 points. That is our reconstruction error. Okay. Vishal,
Is it the loss function?
Something like, don't go in that part, I would say. Here, just think like that. Means just, as I told you, just don't try to mix all the things. And I just want to keep all these things clean. It's like just as I told in the first step, only like I'm using all of you as just novice. Okay. So yeah, Vishal.
Okay. So I'm gonna stop that. I'll share this.
Okay. Okay, just stop there. Yeah. So yeah, as I told you, finally also I will like to say you, like eigenvectors are just like a unique vector representing the direction of largest variance of the data.
So, sir, we are getting more eigenvalue for more variance because of linear transformation.
Yeah, we will get the eigenvectors for corresponding.
So what is the logic, sir, behind it? Whichever has more variance, the eigenvalue will be more.
Which has the as I told you, like eigenvectors represent the direction of the direction of largest variance of the data.
Yeah,
like
that proof you can see in the lecture, or I'll tell you in the end from the lecture notes itself how we are getting after derivating like we can like calculate also how that if I'm having only two lambda, that is lambda 1 and lambda 2, lambda 1 and lambda 2, and lambda 1 is greater than lambda 2. So how lambda 1, how the vector corresponding to lambda 1 will give us a direction having the more like that will maximize the variance, or you can say will minimize the reconstruction error. That you can see in the lecture how we are deriving that the derivation part is there in the lecture. So you can see that how we are coming to a conclusion that lambda, the vector corresponding to the lambda 1 or having the highest value or highest weight of the you can say eigenvalue will correspond to the eigenvector which will maximize the projection of the data, or you can say the minimize the reconstruction error. So I'll tell you one thing. See, this will make you more clear if I'm having sort of two features, F1 and F2, right? And this F1 and F2, that is. And if I'm having data like this, data set like this is some example. This is a simple one so that you can visualize it in a better way. So if I'm having this direction, in this direction, if we have chosen this direction, so we have to find this direction where the variance would be maximum, right? If I have to convert these two features into one dimensional.
Yes, sir.
Right? The variance would be maximum in this direction, right?
Yes,
so
sir.
What we can do, we can take the projection of all the values. So we can what you can say, we can get the xi, new xi delta. This I'm telling about the maximizing the variance. So here I am considering the variance part. So I'll do the reconstruction error also. We'll see it will conclude to a same like optimization problem. Okay. So this is the x delta if I'm converting that. So for example, this is the x1. So how do the projection of this data, like the projection, what is the projection formula normally? If I make this vector, considering this vector as a unit vector means the ui, this will be equals to 1. Okay, and this is the unit vector. So normally the projection of this point, xi point, just for example, xi point on this vector u1 will be what? U1, what you can say, u1 dot xi, like x, if this is x1, then this is xi upon u of this, right?
Yes, sir.
Yeah, or you can say this you can write it in the you can write it in this way, ui transpose of xi, right? This is a new vector. This is the new data point. That is the projection of all our datas on this point, right?
Yes, sir.
Okay. So projection of all this data. And now what we have to do? Normally we have to do what? We have to maximize the variance normally.
Yes, sir.
Okay. So what is the formula for that variance? If I am having calculate, so see, and mean we can calculate directly. How generally we calculate the variance, the data points which are from the mean value. Okay, that we have to maximize. So mean value would be what? X. If I have to calculate the mean, that is 1 upon summation of all those, right?
Yes,
So that
sir.
is simply UI transpose of X. This is mean. Okay, and we can calculate the variance. Variance is what? 1 upon n, and we have to do the summation and we have to subtract it from there, right? So we have to do the summation of all the points and we have to get the difference of these points. So UI transpose X of I minus UI transpose X mean. And we have to do the squaring part. This is our optimization problem. This is the problem that we have to solve. Okay, and we already know that this UI transpose UI is 1. And this is our constant. Okay, this is the given, like because we are considering this as a unit vector also. So this is our problem that we have to solve, and this problem will solve, like that has been discussed in the lecture, and we'll be able to solve this also. Okay, this problem, this is our problem, this is our optimization problem that we have to solve, and we have to get this U1. This U1, we have to get the direction of the U1, or you can say the vector U1 we have to get after solving this. You can solve, okay, after solving this, you will get this U1 if you have to convert this 2D into 1D. Similarly, if I'm having the data set that consisting of thousands of features, okay, and that we have to convert directly into 2D, because the thousand of features, we can't visualize that point. So we can directly convert that into 2D, right? So 2D, so thousand of features can be directly converted to 2D. Okay, and 2D means what? We'll be considering two vectors, U1 and U2, that will be having the maximum variance, or you can say the minimum reconstruction error. So that also we can solve with the help of this similar optimization problem and with the given constant. Okay, with the help of some gradient descent problem and all that we'll discuss in the week 7, 8, 9. Okay, so here we can get the two vectors, the direction where the maximize the vector direction where the variance is maximum, or you can say the reconstruction error is minimum.
Yes,
Okay.
sir.
Yeah, and then we can plot this U1 and U2. Like this is not the exact features, but the mixture of some sort of things is happening, and then we are getting two direction where the variance is maximum, and then that visualization, then we can do the visualization and then divide the data set, or you can say we can get the final result. Okay, so here U1 is after like solving this optimization problem, we'll get to know if this U1 is the eigenvector that is corresponding to the eigenvalues. So maximum eigenvalue, if I am having two eigenvector, lambda greater than lambda 2, so this will correspond to the U1 and this will correspond to the U2. Okay, so
how
lambda,
do you decide how many lambda should we take to, I mean, considering that if you have 1,000 data points,
so
how
out of
do
you
you,
will be having 1,000 lambda.
Yeah, you will get 1,000 lambda. So how do
And
I decide that where to stop?
so see, if I'm having 1,000 lambda, and if I have to convert that part that algorithm will do, if I have to 1,000 lambda, and if I have to convert that into 2-dimensional only, so we'll considering the most weighted lambda and lambda 1 and lambda 2. So like,
Yeah, but how, I mean, how do I come up with that thing that I need only 2?
So that you have to decide, right?
Okay.
If what, like you have to visualize in 2D or 3D or what you want. If you want to, you can see if I'm having 1,000 of dimension, 1,000 of features, right? 1,000 of features you are having. So you just thought of, okay, I'll try to do this in 3 features. Okay, and then I'll see the accuracy of that, how that algorithm is working with the 3-dimensional. If this 3-dimensional, 3 of the lambda values is giving you 95% of the accuracy, like it's like taking out the 95%, it's learning all the 95% of the information grasping. Okay, if you have done with the two features, and if you are getting 94%, because every time the feature, like the accuracy will reduce, because we are taking the lesser features. Okay, so that is also a good part. Like if you are taking only 2 dimensionally and you can visualize everything, and now you are that grasping 94% of the information, then this algorithm is also a pretty good one, right? Because if I'm like we are just converting 3D to 2D and we are getting almost all the data, all the information. So this is also a good, like you can say, algorithm. Okay, so this is how you have to decide, like if you have to decide, okay, I'll do with 4 features and I have to get the 4 best features, we can say, for 2 best features. So you can like that depends on you only.
Okay,
sir. It doesn't come in PCA, sir, because there will be a lot of combinations possible, no, sir? In 1,000, suppose 3, 2, 5, 4. So how do we get, means
what
this
3
part?
to 4?
Means suppose we are we don't know. Suppose we will take, if we take 4 feature, then suppose we are getting 99% accuracy.
Okay.
Then sir, that part we don't know, no sir, without doing.
Yeah,
So how?
after doing only you will know that. It
Yeah.
is like
In
that.
that case, you
so this
have
part,
to take a call.
Yeah,
In that case, you have to take a call
yeah.
as a
Like
machine learning engineer.
as you know that your PCA will reduce your calculation. Okay, so let's say as you told, like you have 1,000 lambda values. Okay, using all the 1,000 lambda value, you get the 100% accuracy, something like that you assume. And if you use just 1 lambda, you get 60% accuracy. You use 2 lambda, top 1 lambda, you got accuracy around 60%. You used 2 lambda, you got accuracy around 80%. You used 3 lambda, you got accuracy around 90%. You used 20 lambda, then you got accuracy around 95%. Then how many lambda you will choose?
but sir, it
Like-
depends on features also. We can reduce also. Suppose if we have chosen 3 feature, we are getting 95%. It
Yeah.
may be that if I will choose 4 feature, then it can reduce also 90% also.
No,
Means it can go
not like
below, no,
that.
sir.
It won't happen like that. That is what this.
Because sir, if suppose I have chosen the some feature which is not too much correlated, then it can reduce also, no, sir.
So see, just you assume. I think you just got some. You just you took some point wrongly. It is like we are. Yeah, yeah. In that 5 steps only, it was written in well manner.
Taking some normal example, like tutorial also not there, then it will be more clear.
Yeah.
Like on problem, if you have.
Okay. Yeah, currently I don't have any problem. Just okay, it's okay. Still, I'll just try to visualize that slide only. Okay, this Hal, can I share that slide?
Yeah. So somebody is asking about the reference, like books and all. So Gilbert Strand is a one book, but he's telling he's not able to connect with the Gilbert Strand also.
So like that we show you this data set. No, is it visual? No.
Yeah.
Yes. So yeah, just assume like we have like 100 dimensions. Okay, like 100 features. Just 5 features we are showing, and yeah, just assume that 100 features are there. Okay, to predict this price. So what this as we told, no, like in PCA we take the top eigenvalues. Okay, so just what eigenvalue is saying that the first eigenvalue which we say that PC1, that is the line which gives you the maximum variance. Okay, here in this graph. Okay, this PC1 is covering the maximum points. Okay, if you have to select one, and that will be the top one. Okay, if that will be PC2, then that will be the second highest eigenvalues. Like this, we sort this eigenvalues, eigenvectors. No, so the point it is always there. Like we sort this. So obviously the first eigenvalues, first eigenvector covers the maximum variance. Okay, so it is all we have sorted here. It means like the first eigenvector will give, if first eigenvector gives 60% accuracy, the second eigenvector will definitely give less than 60. Like that. In the step 5 we did that. Are you able to get that? Hello.
Yeah.
Yeah, that is what we covered in this step 5. We sort the eigenvectors. So obviously the highest eigenvector, the biggest eigenvalue corresponding eigenvector will give the direction of which has the highest variance. So as we go to the lower value of the eigenvalues, that will cover the lesser variance size. So it will be like that only always.
Sir, the eigenvalues are unique, but the eigenvectors are not unique. So if I have different combinations of the eigenvectors, does it make a difference to the PCA? PCA itself calculates that. After that covariance matrix, it transforms that. No, based on no,
that.
Sir, I'm saying suppose if for the eigenvectors, I have x1 plus x2 equal to 0. So I can take 1 minus 1, or I could take minus 1, 1 as well. So that combination, which one I choose to pick, does it make a difference to the final reconstruction error or the PCA that I form, etc.? Because I remember when I was doing the Q inverse lambda Q to find out A, based on what eigenvectors I chose, I would get an A or I wouldn't get an A. So does that make a difference here as well?
I'm not.
Here it will not make any difference.
Okay.
But
is there any way of picking that? Because even in there, when I was doing those problems,
here you don't have to pick, like here you don't have to pick the vectors. So the vector we have to calculate with help of some optimization problem, like gradient descent or
calculation that I'm talking.
Okay, calculation part you're saying.
Sir, like yeah. So while I'm selecting the vector, if I have x1 plus x2 equal to 0, I could to pick up x1 as 1 and x2 as -1, or the other way. I could pick x1 as -1 and x2 as 1. So when we do that, does it make a difference? Because it did make a difference when I was calculating that Q inverse lambda Q.
Okay, so you are
and
asking
I could find out what,
while calculating with the hand, right?
Yeah, while calculating with hand.
Okay, that I have to see that because I can't recall any of the example right now. But yeah, we can. I'll put it on the discourse or on the Saturday. I'll discuss this for sure. Okay, I'll write it down now.
I have put this across on the discourse as well. Like I get different answers, but I haven't got a reply on that. Probably I'll tag you, sir, then.
Yeah, for sure.
I'll do that. Yeah.
Okay, so on Saturday I'll discuss this for sure in the starting of the lecture.
Sure, sir. Thank you. Sir.
If that eigenvector is different, so I will.
Yeah.
Because we can get different sort of eigenvectors.
Yeah, it could be linear combinations, right? So I could get any eigenvector.
Yeah.
So normalization can remove the problem, no?
Yeah, normalization can remove the problem. That is also correct.
Okay, sir.
Yeah, normalization will because sorry. In normalization you have to take every time because if
unit vectors,
Yeah, you'll be having a different vector. So you have to normalize that. You have to divide that with the magnitude. Yeah.
Fine, sir. Okay.
Yeah. So, Vishal, are you going to cover anything else or?
So what is left now? So if you are having any doubt, you can ask till now. PCA, if you are having any sort of doubt.
Like just geometrical interpretation. We haven't discussed anything. Just geometrical interpretation.
We have ask.
Sorry, go ahead.
So what I was saying, we have just covered the geometrical interpretation.
Can you take any data set and explain the 5 steps, sir? If you have.
Sir, we can pick a question from the practice assignment because the solutions are not out yet. So maybe the last question you can pick up and go through all the steps that are there.
Okay, so practice assignment. Okay, I have to see that whether I am able.
Because the solutions are not in place right now. So both the week 5 and week 6.
Okay. So the plan was something like that. Just in this session, we will cover this wide geometrical interpretation part, and we will cover this positive, definite, positive, semi-definite, these 2 6 because we want we want to cover that derivation part in the next session, that derivation part, and then after that at the end we will cover all the questions part, like that question part.
Sir?
Yeah, hello.
Sir, then can you explain the SVD part?
I think for the SVD part, I think Ram will join. He didn't join actually, and we have plans like we want to cover, as I told you at the first step, like we will cover it in the we divided it in the 4 parts. The first part is done. Second part is like this positive, definite, semi-definite part. Okay, so that.
So we'll discuss that positive, definite matrices and function. So what is our plan? Like many of you were asking regarding to discuss all the topics and all. So we'll just circulate the Google form and then you can put the topics that you want to discuss. So we'll cover that in the next session. Okay, so we'll, I guess if you have got the Google form, that is fine. Otherwise, we'll circulate the Google form regarding the topics that you want to visualize, or many of you were asking, you are not able to connect this earlier part at all. So that we'll try to discuss, like SVD, many of you are asking. So SVD, we can cover that in the next session. Okay, so what you can do, will circulate the Google form. You can just write the topics that you want to discuss with us. Okay, so we'll do that in the next session. Okay, is that fine for you? And now,
yes, sir. Yes, sir.
Yeah, so that will work because yeah, that will help everyone, and we'll discuss that solve with us also in the next session, like whatever the question we are having, or we can just share those things to you so that you can go through that point and then you can ask to us. But
Sir,
from the next week, I don't think so you'll face any problem in the watching the lectures also, because different faculty would be teaching. So maybe that will help you from the next week, from the 7th week. So I don't think so there will be any issue regarding the lectures at least.
And as you said, yeah, this is the most like difficult.
Yeah, this was the most like important, what you can say, the difficult one, the proofs and all. From the next week, the more visualization part, or the faculty whoever is teaching in a different book, because many of you are I guess last lecture also you told you're not liking the way just he's writing and explaining, because the many faculties having the different way of teaching. Like many of the person like is not much, like you can say, is prone to the online things. So many of the faculty generally, it's become difficult also for many of the persons to teach in front of camera also. So that depends also from like person to person. Many of the person are very good in delivering the lectures in the online form, but many of the person, I've read with this faculty in IIT Madras and it was good for me. But yeah, for many of like you, it's not like helping you, but it's fine. He'll also take some session in the upcoming weeks. So yeah, that he.
It's like, yeah, it's like summarizing. Sir, is summarizing many things. Okay, something like that only. Like
many a times faculty thinks that you already know many of the concepts.
Yeah.
Okay? Like he presuming that the students are knowing many of the things, and then he's like proving many of the things in sort of like 30 minutes or 45 minutes, and it becomes difficult also. That also I'm understanding. But yeah, what again, like we are here to help you in those things. Like we have started executing the other things. Like earlier we were discussing only the problem sets, but now from now we have thought of okay, we'll discuss each and every things, and then we'll go to the practice and graded assignments, solving those sort of questions. So maybe in this way it will help you a lot. But yeah, so okay, Jimmy, continue that.
Sir, a question before this on PCA.
Yeah.
So let's say we have two features, F1 and F2. F1 has a very high variance and F2 has a very low variance.
Yeah.
But F2 is so important to my data that I can't ignore that variable. So
if that is having a like very less variance, how is that important? Like that value is fixing every time. The less variance means what? The value is every time that is same for all the observation, right? Like if I'm like the blackness of hair, I told you the blackness of that every time I'm taking the data set, every time it's giving me one, like the person is having the black head, like hair. Okay, so that means this features, if this features is having a very less variance, that means this features is not that important, right?
Yeah.
Are you getting my point?
Yeah.
Yeah. So that's why we can remove, or we can like sort of use some PCA algorithm to reduce those features. Okay. And this feature selection also, we do some sort of algorithm where we generally choose the best features. That in that feature selection, how does that work? That will just select in the, that generally works on the permutation and combination. We'll like take out the 4 features out of that 1000, and we'll calculate the so out of 1000 features, that will work on like 1000 C4, and every time it will calculate, and every time it will give you the some different accuracy. But here, out of that 1000 features, we are on the basis of eigenvalue, we are taking out the 4 dimension, where that will help us to calculate the accuracy and all. Okay.
So here we do the SVD of the covariance matrix.
Yeah.
Okay.
Sir, instead of calculating eigenvalue directly, we can arrange on the basis of variance. Because if variance is more, then eigenvalue will be more.
Yeah, that is the that is our problem, that we have to maximize the variance in the direction of some, like in the some direction. In that direction we have to find. That direction can be found out with the help of, after we go through the like you can say the proof part, we'll see in the end, okay, those direction was the eigenvector only. Okay.
But sir, why can't we directly, suppose we have 100 feature, so we know the
okay, so you are
variance
telling me that out of that 100
yeah.
features, you will just go through each features and we'll see the variance, and whichever having is the highest variance, you'll like take it out, and the variance which are the dimension having the least features, you'll remove those things, right? You're asking this point.
Yes, sir, because we are
Very
getting same
difficult,
thing.
right? If you're having millions of features, how will you do that? Every time you go and
No, sir,
go,
we don't have to calculate na eigenvalue.
You are confused between two
calculate the
terms.
eigenvalue, but every time you have to see the variance for all those features. What are the values that is varying? How much the values are varying for these features? Like if that is the feature 1 f1, the values is varying from alpha to beta. For the f2, it is varying from alpha, beta to gamma. Something sort of things you'll see for every points for all the dimensions, and then you will take out the best out of that. So that is very difficult. That is like a human labor is working.
So variance will be in the form of range.
And sir, if we have n number of features, then if we follow that method, then we have to check variance for n square combinations.
Yeah,
like
NC2, that is n into n.
And the thing is, which you are missing, no, I would
No, sir,
say
I'm saying that not for n square. Suppose we have 100 features, so directly we can calculate for the variance for only
that
those
will be
100.
just the variance, no, like you have to see the covariance also, like how it is related with other vectors,
Other features
other
also.
vectors.
That
That
is
is
sir, I got it.
you able to get that, no. So that's
Okay,
why we are
means
plotting that
means whether one
covariance.
feature is also depending on another
Yes.
feature.
Yeah.
That
See,
is
for
what we
example,
are
I'm
doing.
telling you, if I'm having the weight and height of a person, if one
Yeah,
feature is height of a person, one is weight of a person. So these two features are mostly correlated, right?
Yeah,
Like mostly correlated. If some person is having a like height is more, he's having some more weight, right? So both are like very correlated. So we can exclude one features, right?
yes, sir.
Yeah. So that's very.
So because of dependency of the features itself, we
Yes.
we calculate the covariance.
Yeah.
Okay, sir. Thank you, sir.
That's why we told you, like this is your normal axis. Like here, in normal case, the axis is like height, weight, and all. But after PCA, like it's not your normal axis. We call it as a principal component. It doesn't have any physical meaning. It is plotting, like it is just mixing all the things, something like that. Earlier it was independent. Like here we have only weight, here we have only height. This PC1 is combination of both. It can be combination of both, something like that. So yeah, that's why it is plotted on, like after taking the variance, covariance, all those things. And that is what we see, no, like in the covariance matrix, the diagonal is just variance, and all others, other element of that matrix is covariance, like with x1, x2, x1, x3, something like that. Yeah, it's
Yes,
okay.
sir.
Yeah. So I think we are able to visualize that what is that our input to feature matrix, what will be our transform matrix, reduce with reduced dimension, what PCS did, what PCS is doing, how it is doing. That we just told you the steps here. Here we told you the steps and why this step is working. That is covered in the lecture in a very well manner. But yeah, just go through the lecture after, like now, just go through that lecture. If you are able to understand, that is well and good. Otherwise also we will cover that. Okay, initial step, final step, the now just connect the dots, something like that. Okay, so yeah, now we will connect the dots. So yeah, we will cover these two things. And as we talked, like it's difficult to, I would say just one thing. Yeah, it's difficult to create questions, like short questions using these things, like these calculations. It if you will give those type of questions, it will be very long. So obviously, yeah, it is difficult in understanding. It's derivation is difficult. All this, but for question point of view, I will say that yeah, we are bound to make some not so many questions using these things, because it will be very long. Like you have to make the matrix. After that, you have to calculate that covariance matrix, and after that, you have to calculate eigenvalues and corresponding eigenvector and all those things. So it's difficult to create questions. Yeah, and actually not difficult question. It's difficult to create short questions. So yeah, that is the limitations here. But yeah, uh, obviously for understanding purpose, it is very important. As I showed you, that blog, with that article written by that professor, where it is clearly he is clearly saying in harsh words like in more than 90% of the colleges the professors are working, and so many people are working on machine learning. What they are doing, just they are using that code, Python code, and voila, yeah, they are ready to with some data, and they have published the paper, but they don't know what is SVD, what is ASEAN, all these things. So yeah, these things are important because otherwise, yeah, as I showed you that code, no, in this one, whether the code is visible,
No.
No, sir.
like Python collab, okay. You can do that. Just see here, nothing extraordinary is there. Just a few sentences. Just in this one, just see what we did. Just we apply this. This code is enough, like to apply that PCA. Like we imported this PCA, and we just this much only, like PCA dot fit transform. This sentence is enough to do that part. Okay, and yeah, you just see that after that PCA, like how all the data are classified in well manner. Okay, so it is just as simple as it looks. Okay, like that only, this part only. So many people, like almost every people knows this. Okay, but yeah, it is also true that very less people are very less people have the clarity of mathematical part of this, like how it is minimizing this construction error and all. So that is what I'm saying.
Yes, sir. This is a very good point, and these concepts are really like difficult concepts. And within the short time, the professor did a great job. Like, it is not possible to explain everything and to grasp all the concepts within this short time, because these concepts are really difficult. Like with the Lagrangians, and these things are separate things.
Exactly. And in 2 hours, the thing is like he has to cover so many things. It's a bit difficult. And if you want to get this, I am saying, no, like after this, like you will go to the MLT and MLP topics, and you will see that just you will use that code like PCA.fit transform, and you are ready to go. Okay, but this part will be very important in terms of like when you will develop some algorithm, you will do some research work. In that case, these things will be important, and you should know these things. Even I was surprised because I haven't seen the other universities and all, but they meet the PhD guys and all, and he is saying like, yeah, more than 90% people are not aware of these terms of like what is this, what these things are, how it works, something like that. So yeah, that you won't expect, and in same case will happen in ML also, MLP, MLT also. If you want to grasp all these things, understand all these things, you have to work from your side also. Like if you are thinking like although I should not tell it officially, but yeah, I would tell it. If you want to get good grasp on all these topics, you have to work from your side also. Like you have to refer all the what are the available materials and do work on that. Then only you will get able to cover the understand all these things in well manner. Because sir has limitation, like he has to cover the all the things like in a week, almost around 2 to 2.5 hours lectures are there. Okay, but he has to cover so many things.
Yes, in general point of view, it is not at all possible to cover within 2.5 hours.
Yeah, something like that.
So, could you explain eigenvalue part? Like, I have confusion related to this. I'm very new to these concepts.
Okay, eigenvalue, eigenvector.
Yes, sir.
These two things. I would say just because I'm just limiting this lecture because the second part I also want to cover. And if Google Sheet, what Vishal was saying, it will be circulated. Just mention all those topics. We will obviously will make sure that you understand each and every point, because we have time, we have everything. Okay, means we if you are able, you are ready to learn, we will teach that like that. But professor doesn't have that much time, so yeah, he has to do that. Okay, and yeah, just like since 20 minutes left, I just Vishal, will you cover this part or let's start?
Okay, so positive. So eigenvector and eigenvalue has been covered in last session nicely, but okay, it's fine. You can just write it. We'll cover the how generally helps the eigenvalue and how eigenvector generally help us in the matrix, or you can say the like dimensional things and all. So we'll discuss that also if you want. Okay.
And
So now
why?
here,
Yeah, just one point, like why we are just skipping that, because we can directly, instead of talking, we can directly show with that calculation. Like we can show just sample calculation of, like we take some mathematical example and we just show the calculation steps. Okay, that will be, that will give you the more clarity. That's why I said it. Okay, just continue, Vishal.
yeah. So positive definiteness here is a function that vanishes at 0, 0, and strictly that is simple. You can say a half ball. If you are just putting a half ball in the 3D dimension, the 3 dimensional, and that the lower end of that ball is at 0, 0, and for each and every point, like each and every point that is nearby to that 0, 0. So the value for all those points will be positive at all the other points. Okay, that is a simple, like you can say, the meaning of positive definite. How, why that positive definite we are talking about? This is a simple, like you can say, this is a ball. Okay, so many of the problem you'll see in the upcoming lectures, with the help of this ball, this with the help of this positive definite function, we'll be solving a very difficult like problems in neural network, or you can say, yeah, this is the definite positive definite function. This first one, the leftmost part, this, and here at 0, 0, this function is like having the minimum value, and for all the nearest point, the value of the function would be positive, right? So this is the one way to show you this is the positive definite function. This is the function. This can be represented in the form of matrices also. The left one, the right, the second, the middle one is the semi-definite. That means there will be some point where the value, there will be, you can get some axis where all the values for those axes will be 0. Okay, so at x is equal to 0, see, for example, here the values was minimum for that point. So for that semi-definite, that you'll find a line, you can say, you will find a line where all the values will be 0. Okay, and for the indefinite, there will be, so there is no, like you can say, there is no any pattern in the indefinite. So the value can be negative, the value can be positive also after that 0, 0. See, in this first one, the first ball, the definite positive, if I have to solve some problem, for example, this like a mountain, you can say, not mountain, opposite mountain, you can say, or yeah, some sort of valley you can think of. If you are on the valley at this point, okay, on some other on the point at some other point, okay, and if you have to get to, you have to go to the 0, 0, you have to find some minima. Okay, like for example, I've told you, right, we have to solve that optimization problem where you have to get the variance as minimum, sorry, maximize the variance, or reconstruction, you have to minimize the reconstruction error. So if the reconstruction error will come in this form, like in this definite function, so in this form we can solve that function, right? We can just take some how we can solve this, like if I'm just imagine you are on the valley, and at some point you are in the valley and you have to go to the bottom of that valley. Okay, how will you go? You can just find the best step, right? You just find the best step means you will find step means, what you can say, the what you can say, I'm just forgetting that word. Best step means you just have to
minimum effort.
Minimum, you
minimum.
have the minimum effort, how you can go to that point. Okay, 0, 0, that is what you have to get, you have to find. For, like for example, if you have fixed from the value, you have fixed, okay, for that 3 step, this is the best way to go till that step. So you'll find one way. So why, that's why we generally calculate that gradient means what, the step you have to get. Okay, so for 3 or 4 step you'll find the gradient. Okay, again after that 3 step you will think of, okay, this is now the best way to go down. So you'll change the gradient at that point, so you'll find some other way to go down. Okay, so in the similar way you can reach the 0, 0 or the minimum point, or with the help of some constant. Okay, that is how, or that is why we generally read about the positive definiteness. That you will read in the 7th week, how generally the gradient descent works with the help of positive, or you can say this is the convex curve. Okay, so yeah, Jimmy, you can go through that. Yeah. So these are the some, if you are having some sort of this function ax square plus 2bxy plus cx square. So these are the some conditions. So how this condition has came has been discussed in the lecture. If you are having that ac is greater than b square, or and with the one more, a should be greater than 0, then that is a positive definite function. And if that ac is equal to b square and a is greater than 0. So here in this first condition, a greater than 0 will also be there. That is, we have missed that. Okay, so that will be a if at a is greater than 0 and ac if a is greater than 0 and b is ac is greater than b square and a is greater than 0, then you'll be having that function will be positive definite. And if you are having ac is equals to b square and a greater than 0, then that is a positive semi-definite. That means that you'll get some line will be having all the values at 0, all the values will be 0 in that line. And if negative semi-definite means a is less than 0, and you'll be having some saddle point if AC is less than b square. Okay, so yeah, we'll move to the next slide. You can talk this in the form of matrices also. So for the matrices, there are many like criteria to fulfill that. Okay, so this is what we were talking. So if you are having some real symmetric matrix, that means the real will be having all the lambda values will be in the form of real value. If I'm having this fx a square plus bx plus c, so this is the utmost important. Like this is not the necessary. This is the sufficient condition. Like a should be greater than 0 and ac minus b square greater than 0. That if you will solve this ax square plus 2bx plus cy, you'll come to one conclusion: ki at what point and what condition this fx will always be greater than 0. So you'll get this condition: a should be greater than 0 and ac should be greater than b square. And if this both the conditions are fulfilled, so every time you'll see the value of the if you put so if these conditions are fulfilled, so for all the values, all the data sets, all the data points, we'll get the positive function we'll get the positive value of y, or you can say the positive value of the function. So that is generally the positive definite.
So doesn't the previous slide hold for matrices?
Yeah, it looks like that.
So
is
see,
it only for quadratic?
Yes.
So if this is ax square plus 2bx plus cy, so that what will be the matrices? Matrix will be a, b, c, d, right? So here also that will true for C. For the matrices, we'll have to get the determinant should be greater than 0. So there are 4-5 conditions for the matrices also. So if AC minus AC is greater than, what is that, b square. So if I'm having some real symmetric matrices, so what will be the diagonal matrix? The diagonal matrix will be AC, right?
Yeah, AC minus, so that diagonal, the determinant will be the same, right, sir? AC minus b square.
Yeah, so the AC minus b square should be greater than 0. So that is the one condition. If you want to see from that function point of view, that from the function point of view, you got this AC should be greater than b square, right? So that can help you in the matrices also. So in the matrices, now you get to know about the one condition, that the value of the determinant is greater than 0. So that should be a positive definite, right?
Yes,
so,
sir.
And A should be also greater than 0. That means what? That A should see. You can get some other values like A negative also, and you can get to some values where AC will be greater than B square. Like you can just put A negative also, C also negative. So you'll get some A if you will multiply AC. So that in the, like for example, I'm putting A as -3 and C as -6. And B I'll put 7, 7. So that in that condition also AC is greater than B square, right? But that is not positive definite, because A should also be greater than 0. That means what? If you are having 2 cross 2 matrix, so for each value, like this A should be also greater than 0, and then the matrix, and then the determinant of this 2 cross 2 should also be greater than 0. If that is in the form of 3 cross 3, that means A should be greater than 0, and the matrix with 2 dimensions should also be greater than 0. And again, the determinant of that 2 cross 2 matrices should also be greater than 0. And again, for the 3 cross 3 matrices also, the determinant should be greater than 0. Okay, so those 3 conditions will come. Are you getting my point?
Okay, sir.
Yeah. So if that is,
yeah, just continue. Okay.
So that was for the, if you are talking about the matrices form. So there are other some
So
three.
how can we split that function into matrix form? Is there any method ax square plus bx plus cy square equal to 0? How can we make it into this matrix form?
Is that not discussed in the lecture? Okay, Jimmy, continue.
Yeah, that is told you, like we can positive definite or indefinite is in terms of in context of matrix and in context of this matrix. Okay, in context of equations and in context of matrix, these two are different things. Okay, in context of equation, we usually talked about the
Okay,
I
so he's
think
asking how generally we convert that
we
equation
don't
into
need, we
matrices.
not, don't, for that, I think, yeah, I think we calculate now.
See,
Do you by do Hessian matrix is the concept of Hessian will be covered, would have got covered in that part, no? In tutorial actually, yeah. Like what is Hessian matrix? Is it covered?
No.
Okay, it's okay. Like in the next lecture, we will cover that. Next session. Actually,
There
I
is a
do.
question regarding Hessian matrix in some activity question, but
Yeah.
I didn't hear anything, any word in any of the lectures till now. So I don't know whether when
We
it
will
will
cover
come.
that. We will cover that. No worries. We will cover that. It's just like, yeah, first order differentiation. And yeah, just okay, leave it that. Actually, we didn't wanted to cover these thing questions part in this section. Okay, but yeah, still, it's just as Vishal discussed this, like it should be negative, positive, something like that. So, is it a positive definite matrix? Like it's just my question. Take it like, is it a positive definite matrix?
Which one, sir?
This one, 6 2. My screen is visible, no? That.
The right corner.
Yeah,
Yes,
this,
sir. It is a positive definite matrix.
yeah. How many people says that it is a positive definite matrix? Like, can you vote or just comment me something like that, so that we can see like how many population says. Yeah, hello.
Yeah, you're audible.
Yeah, you just comment. We can also see that.
Many of them are saying no. Pradeep has told, sorry, many of them are saying yes.
Yeah.
But somebody has told no. Why no?
Pradeep Sabit. Yeah, Pradeep Sabit. Okay. Yeah. So
will the second pivot come out to be negative or?
Okay. Just okay. We'll cover that. It's okay. Just I just let all people. I want. It's okay since no one is commenting. Okay.
Proportion is same almost.
Yeah. Just Pradeep, you said no. Like it is not positive definite. Just tell me why it is not positive definite. Hello.
Okay, I guess. Okay, somebody else is also there. I'll ask him. Yeah, Sabit is telling this no.
Okay. So
Sambit, can you tell why you have told no?
Sir, as per lecture, the matrix does not match. That is A, B, and B, C. But in your case, 6, 2, 1, 4, 3, 2, and 4 does not match. B does not define here. But the determinant is positive. But as per the rules, A should be greater than 0 and AC minus B square should be greater than 0.
So obviously here AC minus B square is greater
but
than
if
0.
you consider the determinant, then it is positive. But if you match with the exact matrix A, B, and B, C, the B value does not match. That's why I said it's no.
Whatever you are saying, that is correct, but why something like that? Because you just whatever you are at a correct right track. The thing is like a positive definite matrix is just symmetric matrix. The first sentence itself says.
Exactly, sir.
Yeah, it is a symmetric matrix. After that, these conditions come. Like if the matrix
Correct,
is
sir.
symmetric,
Correct, sir.
then yeah, this condition comes. Like it's the determinant should be greater than 0, and yeah, first value should be greater than 0. Something
Sir,
like that.
but why does it have to be symmetric?
Yeah, that is see, positive definite matrix is something like that, as you said, no, this is Ram, this is Syam, something like that. So in that, we call the the definition of positive definite matrix is it is a symmetric matrix for which all eigenvalues are positive, or we can say like yeah, all pivots are positive.
Yeah, you've told the eigenvalue would be positive for the real symmetric matrix that we have covered like in the 4th week or something.
Yeah.
So that is the most important thing.
So it would be related to that functions, right? The X transpose A, X we do. For symmetric matrices, they always come out to be like a bowl shaped.
Yeah, correct.
Yeah. See, I would say one thing, just to take it positive, it's a definition. If once we see that it's a symmetric matrix, and if it is symmetric, then we see that whether the eigenvalues are all eigenvalues are positive or not. Then after that, we decide it is whether it is a positive definite, positive semi-definite, negative definite, all these things. Okay. And what you are saying?
I was actually saying, like, how is being symmetric related to being positive definite?
Okay, so
What is that? Why? Can you repeat that?
How is being symmetric related to being positive definite?
So see, from the starting, we are just see one condition is that the lambda, all the eigenvalues should be real and positive, right? That we know about the real symmetric matrices. Correct?
Yeah, yeah.
That is why every time we are talking about the real symmetric matrices. And whenever you are having some functions, you can, if you are trying to put it in the matrix, you'll get some sort of real symmetric matrix. And if you are getting some real symmetric matrix, that means you are having that eigenvalues greater than 0. If you are able to convert that in the real symmetric matrix, you'll be having some eigenvalues greater than 0, and all that if that value, that if the rank of that matrix is also equals to that features like the n, so then you can say that is a positive definite. Otherwise, you can't say. The first condition itself is not fulfilled.
So you define positive definite as being something like a symmetric matrix, which is like which has this quadratic form, which always is like a bowl.
Exactly. And this quadratic form is for the case when it is 2 dimensional. Okay, if it will be 3 dimensional,
yeah.
Then there will be like just there can be many ways to check whether it's a positive definite matrix or not. But the first condition is only like a matrix which is symmetric, and then whether all the eigenvalues are positive or not. Actually, that you know these terms when from where it comes from the covariance matrix actually. Okay, so it is like it is something like covariance of 1 to 1 1 actually. Covariance of 1 2, covariance of 1 3, covariance of 2 1, covariance of 3 1.
Yeah, and the covariance of 1 2 will always be equal to covariance of 2 1. That's why we are considering real symmetric matrices.
So, sir, I don't know if this was covered in lectures or not, but the function in the 2D case, the bowl which is formed in symmetric positive, like symmetric real case, that the axes of that bowl are governed by the eigenvectors. And so, like, I don't know if that was in the lectures or not. Like, can you like iterate upon that maybe?
Sorry, just repeat whatever you said.
Like, if we do the x transpose a x of a real symmetric matrix, it would come in a quadratic form, which would open upwards, like toward the positive y axis. And if we slice that bowl anywhere, the main axis of that ellipse that forms, like horizontally, if you slice that bowl, the main axis of that ellipse will be the eigenvectors.
Yeah, this just actually whatever you said, no, in the what the pattern of the lecture is like in the sixth week you read about these things. In the 7th week you will read about the gradient and descent part, and in the 8th week again this will come in the high in more detail manner. Like in week 8, these things,
Okay.
like something like that only. And whatever you are saying, that will be that will be in good details. It will be covered. It will be covered in good details with within its 8th week actually. Yeah. So is why I was saying. So it is like what we did. Like we had covariance matrix. No? Then we say that whether this covariance matrix is positive definite, positive semi-definite, or something like that. Okay. So in this case, actually, what happens is like we see that as Vishal said, like covariance 1 2 will be covariance 2 1 equal to covariance 2 1. So, okay. So it is symmetric matrix. So after that, we just say that whether this is positive definite, semi-definite, or negative definite, something like that.
Yeah. So there are if you are having some matrices, there are many methods to to see whether this is a semi like this is a positive definite or not. So there are generally 3 or 4 conditions. One is you can directly plot the function. You can see the energy value, or you can see the value of the function like x transpose whatever the matrix A and X. If that value is always greater than 0, then you can consider that matrices as the positive definite. That is the first thing. The second thing is either of the 4 or 5. Like we can have 3, 4 methods. Either if that is like satisfying the first one condition, so it will satisfy most of like for all the 4 conditions. Okay. Or the one condition is all the eigenvalues are greater than 0. That is the one thing. The second thing is the energy, or you can say the x transpose A into X should be greater than 0. Okay. This is the second method. Or you can, somebody was asking telling about the pivot value. The pivot, if the pivot value is also positive, the pivot value is not talked in the lecture. So you can search on the Google, or you can, I'll tell you the pivot value is generally the if like the lambda 2 upon lambda 1. Sorry, lambda 2 I'm
Sir,
telling. Yeah.
Sorry to interrupt. The pivot actually comes out to be AC minus B square upon A. So that technically that would be AC is greater than B square.
Determinant of that. Yeah.
Exactly. So like that only, like these are the different methods. Based on that, you can calculate this part, whether you can decide whether it's a definite, semi-definite, or indefinite. As I said, the case in case of what it says is like I will cover that also in week 8, and as yeah, week 8 we will meet again. Okay. So what we say is in the definite case, positive definite case, what its geometrical interpretation is, there at the point there would be global minima where all, or you can say there would be all the axes, there would be a point where all the axes are minimum, giving the minimum value. And in semi-definite case, we are saying that there would be at least one axis where the points are minimum. And in semi-indefinite, we can't say anything about these axes. Okay, if you are getting this my words in this lecture, that's okay. Otherwise, in week 8 you will be able to understand whatever I'm saying here. Yeah, more or less. Yeah, these things were covered. Okay. So I think again we are here only, like, yeah, this part covered. This what we'll get output. Yeah, that is also covered. How part is done. So why it works. This part maybe we will cover in maybe not. We will cover, definitely cover in the next session.
Yeah.
And yeah, next session we will do that part, and yeah, we will cover the questions part.
So one request to everyone, if you are having any point, like any difficulty in any topics, like somebody was asking eigenvector, that has been discussed, but that also you can put, we'll try to discuss that in like minimum time, that so that will help you, because we are having sort of time, so we can discuss all those points. If you are having problem in SBD, you can just write the topic's name, so that we can just take one session of 2-3 hours and we'll discuss all those points. So that will clarify all the doubt, whatever you are having till now. Okay, and then we can discuss the practice session, or we can next session we'll take some examples that you are asking, and then we'll try to solve. Like we'll discuss the solve with instructor for the 6th week in the next lecture, so that I'll first you'll try to solve that, and if you are not able to, then we'll try to solve that. That will help you. Okay, so that may help you in one or other way. Okay, so now I guess we have discussed the PCA parts, like the implementation, the geometrical interpretation. We have not discussed the proof, how we are getting the eigenvector and eigenvalue, how we are getting the eigen, that vector that will help, that is generally where the maximum variance is, or having the list reconstruction error. That now you can see the lecture from the 3rd part. You'll be able to, I guess, relate that everything. Now you are in that position to get everything, okay, how that has been discussed in the lecture. Okay, so that may help you to go through the proof of those parts, and then also if you're not getting, we'll discuss in the next lecture. So till now what you can do, I'll share you the Google form. You can put the topics that you are facing the problem, and then we'll try to discuss in the, every time we'll do the same part. We'll discuss all the concepts of this of this week's, and then in the next lecture we'll try to like give you the Google form, and whatever the problem you'll tell, we'll discuss that part, and then we'll go through the solve with instructor, where you'll be able to solve some question, and that will help you to grasp or how to solve those parts. Okay, so is that fine for everyone? So we'll solve all the like slides also and the Google Colab also. Maybe that will help you. Okay, so now is that fine for everyone? Can somebody tell?
Yes.
Yes, sir.
Yeah.
So could you please share the assignment solutions as well? I mean, the practice assignment.
Yeah. So I'll share it today itself. Week 5 and week 6 will share also. And if you are facing any doubt, you can put it on the discourse on then or we'll discuss in the next lecture also. Okay.
Because sir, I haven't been able to solve the graded assignment of week 5 because I didn't understand SPD well. So probably the practice assignment solutions.
Saturday we'll discuss for sure. We'll discuss the SPD part in total like elaboration. So on Saturday, and we'll try to discuss like 1-2 problem related to that. Maybe that will help you. And I'll share the solution also for the week 5 and 6 both of the practice assignments. Okay, just try to solve that. Otherwise, we'll discuss in the next lecture.
Sure, sir. Thank you.
So please the PCA derivation too, if possible.
Okay, I'll cover that PCA derivation also. Till now, we have came to a conclusion how we are getting with what is the cost, like what is the optimization problem we are facing. Next lecture we'll solve the optimization problem and we'll get to know regarding how we are coming to a conclusion how that eigenvector and eigenvalues is helping us. Okay, is that fine? But one request, you can just go through the lecture also. You can just go through the slide or the PPTs, whatever sir has written. Maybe if that is not helping you, okay, we'll discuss in the next lecture. Otherwise, everyone should watch the lecture at least once. If you're not,
sir, I have tried. I was going through the third lecture. I'm not able to follow clearly. So if you can just discuss like the one approach, like the linear algebra approach, the projection one, that would be fine too.
Okay. Anything I'll discuss, like both of the thing I'll discuss and we'll come to the same conclusion by the variance or you can say the reconstruction part. In both the like cases, optimization problem will come to only one conclusion, that is the eigen values on eigenvector. Yeah. Okay then.
Yeah, so I hope you guys enjoyed this lecture and we would have able to add some values. And at least as I put in the first step, like we were able to deliver whatever we want. Are we able to deliver whatever we wanted?
Yes, sir. Yes, thank you, sir. Thank you very much.
Yeah. So yeah, we will do. We'll try to in the next lecture we will try to simplify the derivations, and after that we will go to that question part, like how we can solve all the questions in minimum time and with minimum effort.
Okay, then thank you.
And
thank you everyone.
Thank you. And as Ashish was asking, when we will share this with Google Form. I think if it is not shared yet, it will be shared soon.
Yeah, today itself we'll share that. And whatever the minimum to minimum, like whatever if the doubt is very minimal also, that also you can write it there. Okay, so we'll try to sort out everything in the next lecture. Okay.
Yeah. So I hope.
Thank you everyone for joining the session. I guess.
Thank you, sir.
Yeah.
Thanks a lot, sir.
Thank you. Weakness is there. Are you messaging? Are you messaging in the group regarding the session?
What session?
Weakness.
Okay. Okay, we'll leave then.
Yeah.